The most important thing we need to make sure we're coming to terms with is this notion of open life history traits in this sea. Open life history types of populations exist on land, but we typically think of terrestrial things as more closed, whereas the majority of things in the ocean tend towards a more open population dynamic. And so what I mean by that is simply this, is that the default thinking, particularly of exploited species, such as this sort of cartoon rockfish here, what we see is we have relatively site-attached adults. That could mean either physically attached, like a barnacle actually has glued his head to the rock and the adult doesn't move once the adult settles down. Or it could mean something like this fish that is not technically glued to the reef, let's say, and it can move around, but it generally moves around on that reef. It's not going to go up and down the coast, let's say. The babies, the propagules that the barnacle is producing, that the fish are producing, the eggs and sperm, and then once those eggs and sperm are fertilized, those things often disperse. They float, they move. Maybe they land on that same reef where he or her, or she or he are, I don't know, up too late last night, where they are residing. I'll say it that way. But maybe those propagules go a mile up the coast, or 2 miles up the coast, or 50 miles up the coast, or across the Pacific basin. So that decoupling of obvious local generation of individuals and obvious local input of individuals to that reef area, let's say, is a so-called open, more open type of population. And we typically talk about that as a bipartite life history, meaning a two-part life history, meaning there's something distinct about how the adults behave and engage with their environment, and how the developing or juvenile individuals interact with their environment. And so again, classically it would be a fish whose adult dynamics are dictated by what is going on that reef. How many predators are there? How many competitors are there? How many cracks in the rock exist where this guy can go in and hide? Reef-based processes, local-based processes. What's going to influence where the little dispersing individuals go? Currents, oceanographic patterns, stuff like that, right? So we therefore have these bipartite life history dynamics in the ocean, and that makes designating protected areas more complicated on average than in a terrestrial environment where we would say we want more of these pine trees, let's say, or more of this deer population. We want this deer population to increase. And so therefore we're going to carve out this valley, and we're going to say nobody can hunt in this valley. And then generally, if we want to know how many deer are in that valley, we go count the number of pregnant moms in that valley in springtime. And that's going to be a pretty good indicator of how many babies are going to be in that valley, several months later. If we go out and count the number of pregnant fish on Reef X, that may be strongly related to how many babies we see in a few months on that reef. More typically, pretty unrelated, or oftentimes unrelated to how many babies we see. Okay, so that bipartite life history is really key. So again, we have the sedentary phase and this more dispersive phase. That's the first thing. Second thing, size with fish, let's say, and we're oftentimes talking about fish, size often, but not just fish, but size often has a strong influence on fecundity. So this is a classic illustration that everybody has used since it came out in this report. But what you see is we have this rockfish, and so the adult is represented by the red adult fish at the top. And then the juvenile fish underneath represent how many eggs or how many juveniles this individual is capable of producing, how many eggs, which would then turn into juveniles. And what you see is it's not a linear relationship, right? If it was a linear relationship, as this fish, say on the left, were to, let's say, double in size, to be a bit bigger than the one on the right, we would expect it to be, if it was linear, double. So we'd expect the fish on the left to produce something like 150,000 potential offspring, and if we doubled it, maybe 300,000 potential offspring. What we see is when an individual gets not even double that size, they're producing orders of magnitude more babies. And fish have either indeterminate growth or what's called plastic growth. So fish can get bigger faster or bigger a little bit slower. And so they can respond to the conditions, not just their physiological determination in terms of how big they get or whatever, but actually the environment can be a strong influencer on their size. So bipartite life history, size influencing fecundity. And then take a step back. Again, as we touched on last time, we've had this notion, we, the conservation community, have had this notion of biological reserves for quite some time. The basic assumption is that if we want to protect a well-functioning, healthy ecosystem, kicking people out is a key way to do that, right? So don't let people fish here. Don't let people cut down the trees here. Don't let people, mine here. And that really directly emerges out of there's a very American notion, just as is wilderness. And a lot of our thinking about this emerges from our cultural conception of what wilderness is and idealized nature. So idealized nature for most of us in America is a condition where people are removed, or people are absent, or people are very, very minimal, right? We go to the islands, we go out camping the Sespe to be away from people, right? And to see nature in its grandeur, which means no buildings, no roads, that kind of stuff. And so all we've done is basically taken this idea of biological reserves, turned it into this notion of kind of a park, and then we've taken that idea of a park and put it under water or in the coastal zone, in an estuary or something. So here's a quote about why we might need marine reserves. So I'll read them. First one is from a guy named George Coons. During my recent visit to Santa Catalina Island, I was deeply impressed with the threatened danger to the commercial and valued sport-giving fisheries at the island. The island, for 3 or 4 miles offshore, is the spawning ground of the valuable food fishes of Southern California, and particularly of Los Angeles, and that this region should be protected absolutely from all kinds of nets or lines handled for commercial or market purposes. And then a little bit later, this quote is, fishing around Catalina Island over the previous 30 years decreased stocks to the extent that the supply of fish, they're saying, the supply has dropped off to a menacing extent. Menacing. Ooh, look at that. Due to lack of laws, lack of protection, and overfishing. The angling here in year blank to year blank was the most remarkable in the world. But with the coming of powerboats, seines, trawls, and other nets, the fisheries began to decrease until it was evident that something must be done. The most menacing danger was the alien who attached a gill net to the kelp and ran it out to sea. 50 such nets have been counted in 1.5 miles. So my question to you is, what years should we put in here?
This is like 1920s.
1920s. Good guess. The first one is 1912. The years these guys are talking about, the bottom report is 1913, and the years they're talking about is 1886 to 1900. So there were some clues in there that wasn't right. Talking about aliens, right, and sport-giving fisheries, right, that kind of stuff. But the point is, we have been, as we've talked about before, but yet more evidence that we've been influencing our fisheries, but not just fisheries theoretically off in some European whatever somewhere, right here in Southern California, right here off the Ventura coast, right here off the Los Angeles coast, right here off the Santa Barbara coast for the last, more than a century, well over a century. And so, a century ago, more than a century ago, these folks were saying, oh my God, it's so bad now. Right? It was so much better back then. It was so great until we started messing with it. And oh my God, we have so much, activity here. And note that they're worried about technology in 1913, before we hit the big World War II change everything as we know it type area. And so the result of this effort was to establish a 3 nautical mile reserve around Catalina, which banned all nets, meaning these types of gill nets. But that was short-lived. So it went into effect, and then the commercial, the fishing industry basically said, no, we like to catch fish, so you should stop that. So a very forward-thinking effort to enact what we would now call an MPA, but it sort of burbled up and then got whacked back down. This is what that looked like back in the day. So this is again, we last time we mentioned black sea bass. This is a black sea bass, or a giant sea bass, we're supposed to call them now. And check out that lady caught that fish, man, in her black dress. Oh yes, I've got large sea bass, right? And so the dude's like, damn, another big fish I got to pull out of the water, right? That above picture is actually from Mexican waters, but that's a white sea bass on the right, just showing the size. Again, lady pulled it in her nice skirt, right? So good haul for the day. That would be a massive fish. That would be sort of a world record now if we were to get that fish. We talked last time about changing sizes of fish over time. And then this picture on the bottom, it just illustrates, picture, this was from 1910. These guys, in this case, they're getting bait fish, so they're trying to get these athrinids, these little sardine kind of fish from the shore. And you can just see in the background, here's a boat with a net. All these guys are getting their bait before they go fishing. So, large fishing pressure even, 100 years ago. So I haven't updated the slide in a couple years, but it's hard to run these numbers every year. But this, again, proves a point we discussed last time. So marine protected area, you know what that means, that's MPA. In general, our marine protected areas to date, our California example is a significant departure from that. The efforts going on in places like New Zealand are a departure from that, but currently, most of our marine protected areas were not designed. They just sort of fell into our lap. So, for example, one year I was at a conference with a gentleman, and we were talking in a social context, and he was talking about this great reserve around Cape Canaveral in Florida. It was a reserve because the military said, hey, we're shooting rockets up to the moon and defense satellites and stuff, so you can't come close to, this part of Florida. So that wasn't picked to be the best possible fishing area or whatever, but it's become an incredibly fantastic fishing area because it has low fishing pressure, right? So it's in effect an MPA, and that's more typical than not. Again, this number's gone up a bit, and this doesn't reflect some of our most recent numbers, but I think it proves the point, which is that we have a good number of reserves in a good number of countries, but the majority of these reserves are small. Okay, not the mean size, the median size is about 4 square kilometers. Because we have a subset, we'll end today with a quick discussion or touching on what we call large scale, people have different words for them, we haven't settled on the term, but one term is large scale marine protected areas. And these are things like Papa here in Hawaii, The Kiribati, the Phoenix Island, which is actually a paper park. It only really exists on paper. And they've won all these international awards and all this great stuff, but it's actually baloney. There's essentially no protection. But when you look at it on paper, at least, it looks like, oh my God, it's a huge reserve. So setting the aside whether they work or not question, we have some that are quite large. Most, though, are much smaller. Elkhorn Slough is a salt marsh protected area up in the middle of Monterey Bay. Carmel Bay, very close by. Wrigley Marine Reserve, that's where I did my PhD work at, right? That was the one I mentioned off of Catalina. That's relatively well enforced, and that's, very small. So key thing here is median size is about 4 kilometers. Mean is about 44, but realize that mean is very skewed by a few large reserves. Most are very small, or comparatively small. Okay, so do these things work? Is it at least theoretically possible that this tool of, say, disallowing or restricting or limiting to some extent exploitation effort, fishing effort, can lead to the recovery of some of these populations? So this story is from that same. This figure is from that same report as that fish illustration I showed you a little bit ago. So this is, and you guys have read a similar report in your readings, but this is looking at a couple different things. Biomass, and biomass is a typical way. We're just starting to talk about this, but you might have figured this out from some of our readings. Biomass is a typical way fisheries folks talk about fish populations. Partly comes from history because they weigh fish when they come to dock, so they have a weight. But it also reflects that it's sort of an akin to numbers, but it's not exactly numbers. It's biomass. But clearly, the more fish we have, the larger the biomass, generally speaking, will be. And so this question is, okay, so these guys did a meta-analysis, which is an analysis of analyses. So we collected a bunch of papers and read all the papers, had you guys read them, had you guys put them in an Excel table, and went through and sort of then did the statistics on the results from the papers. So they looked at 124 marine protected areas from all around the world. Some were in Africa, some were in the Pacific, all around. And they said, okay, so they started the reserve, and then we had some amount of the ecological condition was X, and then at some point in the future they measured it, which is what was published in these studies, and they found that it had changed to Y. In some cases it had decreased. Most cases it went up. And so here you go. So if the change, and this is all standardized to the percentage change, because different amounts of biomass and et cetera exist in different areas to start with. So we just talk about the relative change in each one. So 100% change would be to double, right, et cetera. So what we see is the dots are all of the actual values, all the numbers reported from the studies, and then the green bar represents the mean value. Biomass, density, which is number of individuals per unit area, size, which is the average size or the overall size of the fish or the other exploited species, and then diversity. So this could generally this is probably species richness, but it could be other measures of diversity. And what you see is biomass goes up, right? Almost 500%. Huge impact on biomass. So you put an MPA, and within some period of years, there's more grams of, say, fish tissue inside that area than there was before. Pretty consistent response. And again, you guys saw this in some of your other papers. And then same thing. Density goes up, although a much greater spread in the response. And I just note, this is an axis break, right? So this is not a linear scale. This is to accommodate these much higher values. So there's some areas where these marine protected areas have done incredibly well, like orders of magnitude, massive, many orders of magnitude greater impact. there's also some sites where they have degraded. They've gotten even worse. So we see biomass, boom, quick. Density, also fairly large. Size, also a positive change, but less massive, right? We wouldn't expect the size of fish to increase by 2,000% because that's not realistic. That's not biologically realistic. And then diversity also has a positive trend. So this says that at least it's possible for MPAs to produce a result of improved biomass, improved ecological functioning, presumably, etc. So here's a story from one of our oldest reserves in the California Channel Islands. This is one on Anacapa. This is this one reserve on the far eastern end. And this was established in the 70s, this particular reserve. And this is what we saw. So we have areas that were inside the reserve, areas that were outside the reserve. And so this is what we see. So this is a relative scale. In this case, let me explain over here first. Okay, so what we would think would happen in a typical reserve, or just let me say this, we think this would happen in a fished area. We take away a lot of the lobster. Lobster are huge predators. You guys generally don't think of lobsters as predators, but they're quite big. They eat, among other things, little baby urchins. So if we take away a lot of the lobster, there are less lobster to eat the little baby urchins. So that means the urchins are more likely to grow or increase in population size. And the urchins can get to their normal background size, and then at times they form what we call an urchin barren, barren, urchin barren, and they just get super hungry and they go and they ravage the kelp, and they knock the kelp down. And this is a natural cycle. It's been going on forever, but the frequency at which it's happening is strongly influenced by people these days. So we have these urchin bears, and these urchin barons go crazy. So normally urchins are hiding at daytime, because when they come out in the daytime, fish eat them. Sheephead, other things will just mack them down. So they usually only come out of their home scar. They have a little divot they usually go back to every night. They come out of their homes at night, and then just before the sun starts to come up, they run back and they go back and hide. And they have these giant spines, obviously, to not get eaten by fish and other things. An urchin barren condition is a period where they start to starve for whatever reason. Could be a bad kelp year, could be warm water temperatures killing the kelp, whatever, because these guys are detritivores, so they'll eat broken off pieces of algae. Urchin barren forms, and these guys the system switches. It's a different state of the ecosystem. Now they're out in the daytime, and they're essentially a continuous front, and they're starving. They're like a 13-year-old boy. Eat everything. And they just mow across the land, literally like a lawnmower. And they either eat directly or they rub against and break off kelp. And so in an urchin barren condition, you have much fewer kelp individuals. You have a much less three-dimensionally complex reef system. Everything on our local reefs, or just about everything, is driven by this kelp force. It's an absolutely foundational keystone species. You take away the kelp, you take away food resources, you take away habitat, you take away places to hide, places to forage, everything changes. So when we take the kelp away, everything goes down. Fish biomass, fish diversity, just everything. On the left is the illustration inside the typical marine reserve condition, which is we're not allowed to fish the lobster. And so the lobster can be abundant, and the lobster can keep the urchin populations in check. And those urchin populations in check, therefore, allow there to be relatively abundant kelp and relatively diverse reef systems. So that's a bit of a simplification. Obviously, in the fished area, we now fish for uni. We fish for urchins to sell primarily the sushi market in Asia. And so it's not as straightforward as this would imply, because we can, not only can we knock these guys down, we can knock these guys down too, but we'll set that aside for a minute. So what you see over here is this is the long-term change or long-term dynamic in this system. So the blue, again, is the fished area. The green is the marine reserve. And what we see is there's always good years and bad years, no matter where we are. Some years it's better for the right conditions, got a lot of babies coming in, whatever the case may be. Other years are different. But even with that background variation, we see that still abundances in the reserve system generally outperform those in the fished area. So that says that, hey, these reserves can work. There are some problems. And can you think of any of the problems with this particular data set? Or potential problems with this data set? Too early? You work on your paper too late last night? Am I showing you a mean value of that green line? Vanessa? No. It is the value for that year. So this is one reserve versus the area outside the reserve. Okay? This doesn't make it wrong per se, but it means it's not necessarily representative of the whole system, of reserves in general, right? Everybody following me? What if we just happen to, so hey, marine reserves, the reserve, the MPA is better than the fished area. Really? Or did I pick the best possible area for fish and call that a reserve? So would this work as well if I picked the crappiest place on the island for... Right, probably not. Right. So again, this gets to that area of, it doesn't mean that we were wrong to create a protected area here, but it means when we interpret the results, when these places were not established randomly, we can't really treat it as a random experiment, right? So again, it doesn't mean this is wrong, but it means there's some caveats with this. So that's why we need to make sure we have more data from more sites, replication, etc. So that means that takes us to essentially the framework that we talked about last time in terms of the Marine Life Protection Act, and how we might go about doing that more robustly as opposed to just some random one-off because some scientist wanted this or because some government rocket launching entity wanted technology to go there. How can we do this more robustly? So to do it really well in terms of a network, meaning a series of individual protected areas, what are the things we might want to consider? So here are the four most, I would say, important things in terms of the science side of stuff. The first is location. Where are we going to put this particular MPA? How big is it going to be? Since we're going to have more than one, how far apart should those protected areas be from one another? And then fourthly, how easy is it to enforce? How easy is it to make sure that this thing will take place? Now in the Cook Islands, when folks say, hey, this is the deal, in those cases it's a much smaller community. There's a lot of social pressure to follow the rules. And then in some cases there's some people that don't care about that and they just kind of do it. And there's other social pressure that comes into play then. But it's okay. So we have location, size, spacing, and enforcement. A criteria we might use to one of many possible ones for location is, hey, let's make sure that we pick it in an area that, let's say if we're worried about fish that live in kelp beds, let's make sure we have some areas that, at least some of our areas, are in kelp beds. So representation. How big should this area be? Well, that should be one of the most obvious things, is how big do the critters that are within this potentially protected zone move? So if we have something like a whale, that moves from Alaska to Hawaii, making a whale reserve that's 20 miles by 20 miles, it's probably not going to do it, right? Because the whale is going to be in there for only a small amount of time, and it's going to spend the lion's share of its life cycle outside of the protection. So what's the point of that, right? So there's a lot of attention to how animals move, and mostly as adults, and how do we figure that out? Next one is spacing. That while size, the appropriate size of the MPA is generally dictated by how big the adults can move. Spacing, area between these, is how far do critters disperse? How far does the dispersive life history stage, how far do the larvae go, typically? And then enforcement is, as we talked about last time, is it very clear? It goes from point X to point Y, this clear promontory on this bluff, etc. And is there money to actually enforce it? Okay, and I should also say, for purposes of this theory discussion going forward here, when I say marine protected area, we're talking about fishery restrictions, just so I'm completely clear. And unless I say differently, we're talking about a no-take MPA. So in other words, one that says you can't take any fish. This isn't a partial fish. Commercial guys can't, recreational guys can. It's easier to talk about just complete closures to see the effects of stuff. All right, so here we have a couple questions. These might be perfect midterm questions. Wow, look at that. Those are really good. So some current questions that we could apply to this discussion include, are percent protection targets useful in marine environments? So that means, how much should we set aside? How much? 10% of the ocean, 5% of the ocean, 1% of the ocean, 30% of the ocean, whatever. So are those a useful guide to policy folks in a coastal marine management context? How large should any one reserve be? I know they'll vary in size, but is there sort of a clear rule of thumb we should follow? Perhaps most importantly, I probably should have this be question number one. Do marine protected areas increase fishery yields outside of the reserve? This is the bargain. This is the claim that has been made by everyone, or just about everyone. The data that I showed you before, that was within this marine protected area before versus after. So it's pretty clear that stuff will work well inside the area of management. But rarely do people say, that's all we care about. Usually they say, hey, fisherman dude, if you allow us to close off this reef, it might hurt you in the short term because maybe you can't fish there. But over the long term, it's going to be much better. It's going to stabilize all the fish populations in the area, and you'll benefit. You'll benefit by fish leaking outside the reserve, right? And then when they go outside the reserve, you can fish those guys. So implicit in that is this notion that fishery yields outside of the designated MPA are going to increase over time. And then, again, another very practical one from our coastal marine management context. Yes, as we discussed, we had these historic pre-existing MPAs or pre-existing protected areas. Can we use them, or is it better to delete everything, and should we have started from scratch with that Marine Life Protection Act process? We can go about answering these questions in two ways, as we could with just almost any question. We can actually go out and measure the real world, or we could model stuff. Clearly, empirical data is the best, because that's what's going on in the actual real world with real populations in real settings. We have some experience with existing marine protected areas. I just shown you that data, for example, from Anacapa. But as I alluded to with that study, we have very few. There's more. We're getting to have some more. But generally speaking, we have few controlled, truly manipulative experiments that would allow us to test a lot of this underlying theory, a lot of these underlying assumptions. So oftentimes what we relied heavily on for our MLPA process, for example, are modeling exercises. So models allow, so again, any model is a simplification of nature. Any model is unreal. That doesn't mean it's horrible or bad, it just means it's a simplification of what actually goes on in the real world. Models, though, can allow us to ask some what-if questions. Okay, what if we added another reserve? What if we spaced them only 3 miles, right? And given our assumptions, what do we think is probably going to happen years down the road? Generally speaking, the models that we use for MPA planning processes are the model is only as good as the data that goes into the model and the assumptions that create the structure of the model. And because we don't have a lot of historic empirical data, we don't have a lot of really good data to go into this. Similarly, we don't have a huge amount of data necessarily on life history of a lot of species, how long they spend in the plankton, etc. As a consequence, sorry, I was up all night. As a consequence, these models are usually quite conservative. Doesn't make them wrong, it just means they're usually pretty conservative. Okay, let's start with this, and if we want to take a little break and stretch, you guys can take a little stretch. So I mentioned this percent protection targets. What is that? What was that? So this is a approach that really started in the early 90s and caught fire and has become a big thing. So the first formal large-scale notion of this came from the International Union for the Conservation of Nature, the international NGO, which is sort of quasi-associated with the UN, but is separate. And these guys said more than 20 years ago, hey, everybody should have 10% of each of their ecosystem, be it on land, be it on underwater, set aside in some type of protected status. The American Academy of Sciences did a significant study in 1997, and their main conclusion was that we should have 20 of, this is talking about marine protected areas now, of MPAs, 20% of the world's ocean should be in a no-take reserve by 2020. And then the World Parks Congress suggested that no-take should be larger than that, maybe as much as about a third. So I'll tell you where the 20% came from. The 20% came from, at least was strongly influenced by the experience in Florida. So experience in Florida, do I have a picture of this? No, okay. So the story in Florida was that meeting I said I was at. I was talking to this guy, and we were having a few carbonated beverages, and we're talking about stuff, and which is usually where you learn the most stuff. And so he's this great guy, a wonderful fisher, worked for the state agency that manages fisheries in Florida, and he'd been monitoring this area by Cape Canaveral for a long time and showing tremendous things. So all the great sport fishing records and stuff were all clustered around or very close to this area. So we started talking. So clearly, Florida said, "Oh man, these marine protected areas might be really helpful for our fish populations." They started looking into them, and he was essentially charged with developing a plan in the 90s. And so they were trying to figure out how much of our land, how much of our waterways in Florida should we make a protected area. And again, not a lot of empirical guidance, right? There's some implications, some suggestions, but not a lot of place. So they said, hey, 10%. 10%, maybe. This is the late 90s. How about, and to make it passable by the legislature, They're trying to get some governing legislation on this. They wanted to make it obvious so that even a elected official at the state level in Florida could understand what was going on, right? Okay, maybe we should pause here.